All right, today we're going to be doing electromagnetic waves. So we're going to see how electromagnetic waves are very similar to what we did in chapters 14, 15, and 16, but there are some things that are a little bit different. As we already saw, we know electromagnetic waves don't need a medium to travel in, so we're going to see how this affects things today. So the first and most obvious electromagnetic wave is obviously light. So we all know that light, radio waves, microwaves are all examples of electromagnetic waves. Now, light or any electromagnetic wave will travel at 3 times 10 to the 8 meters per second through a vacuum, through empty space. And the important thing here is that light does not need a medium to travel. So as we saw in chapter 15 and 16, our waves needed a medium to travel through, right? We either needed a string or we needed air for our sound wave to travel. EM waves are not like that. They can travel through completely empty vacuum space. They don't need a medium at all to travel, which is very unique. And we're going to be seeing some applications of electromagnetic waves on Thursday, but obviously so many things that we use in our everyday life are using electromagnetic waves, your cell phone, computer, Wi-Fi as we have down here, those bullet trains at CERN where we have that huge particle accelerator in Geneva. It uses these huge electromagnets to keep the particle beam moving in a circle. And then obviously the sun. We know that the sun sends electromagnetic waves from itself to Earth. So the current theory of electromagnetism was developed by James Clerk Maxwell in about 1861 to 1864. So he was the first to propose that electricity and magnetism were actually the same phenomena and that they were also a light wave, that they moved at the speed of light. So this was actually a really interesting time in physics history because this was the first time that we really unified previously completely separate areas of physics into a single force. So this was really the first time that this happened, and this really laid the groundwork also for relativity. So this is kind of where our physics revolution, with quantum and everything, really started, was with Maxwell's equations. So here's Maxwell and his wife, and I know that you guys said you wanted more dogs. So here is his dog, and I don't know if they airbrushed its face or something, but I've never seen a dog with such a human-like face. But anyway, I thought that was funny, so I picked that picture. So that's Maxwell and his dog and his wife. So when Maxwell originally wrote his equations, he actually wrote what we now have as 4 Maxwell's equations. He actually wrote them as 20 separate equations because vector calculus wasn't developed yet. So if you've taken multivariable calculus, you've seen the divergence, you've seen the curl. All of us have even seen just a vector as a 3 components, right? One for each direction. They didn't have that yet, so that wasn't developed yet. So he wrote his equations as 20 separate equations, basically one for each component, because we didn't have the, what is the word? Because that terminology or how we write vectors wasn't developed yet. So here are all 20 equations, so it's really tiny. But these are all, if you count them, there's 20 equations here. And so luckily, Oliver Heaviside actually came along and helped sort of formalize vector notation and put Maxwell's equations into the forms that we know today. So we were able to condense all 20 of these equations into the 4 that we know here for Maxwell's equations, which you probably saw in 7D. And his original equations were also done in terms of quaternions. So now if you haven't heard of a quaternion, it's actually really cool. I know we have a couple of math majors in the class, so I would highly recommend looking into quaternions. There are some really good number file videos and some 3 blue, 1 brown videos about it. Basically, a quaternion is just a higher complex number. So we know we have the real numbers like 1, 2, 3, 4. We have then complex numbers. And then beyond that, we have quaternions, which have 3 complex numbers, right? So normally we have 1 complex number I, and quaternions have 3 complex numbers. They have I, J, and K. So they're kind of like one step beyond the complex numbers. And that's actually where our vector notation, where we have I hat, J hat, and K hat, those actually come from the quaternions. So it's very interesting, historical math physics period when all this stuff was developed. So I'd highly recommend looking at some of those videos if you're interested in that. And now we also have, beyond, this is the differential form of Maxwell's equations because it's written in terms of the divergence and the curl. There are also a lot of other ways to write Maxwell's equations. Here are Maxwell's equations in terms of differential geometry. So there's, like I said, there's a lot of different ways to write the same thing. They all mean the same thing at the end of the day. They all correspond to the same physics, but we have just a lot of different sort of languages for writing Maxwell's equations. So you have the differential geometry form, you have the relativistic form, which is like the language of relativity and Einstein came up with. Then you have the differential form here. So there's a lot of different ways to write the same thing. And now what I personally think is the most interesting thing about Maxwell's equations is that they're already relativistic. So relativity wasn't developed, Einstein didn't come up with it until like 1903 or 1905, something like that. So we didn't have relativity until then. However, so Maxwell had never heard of relativity. That thought really never crossed his mind. But his equations still are relativistic. So once we developed relativity, you actually didn't have to change Maxwell's equations at all to make them relativistic. So for example, like, F equals ma, when we start doing that in relativity, things change a little bit. And Maxwell's equations were actually what sort of inspired Einstein for his theory of relativity. And you can kind of see it this way. Now, I'm simplifying this a lot and I'm skipping over some little details, but this is kind of just a way to get an idea for why Maxwell's equations are already relativistic. So the point of relativity is that there's no absolute reference frame. So one way to think of this a little bit is, let's say I have a wire, and we know that our wire, if it's carrying a current, it's carried with electrons. So let's say we have an electron in our wire. And now let's say that these electrons are moving down the wire at some velocity v, whatever that is. Now let's say that I am also moving parallel to the wire with that same velocity v. So we're down here, and we're also moving with velocity v. So that means to us, let's say there's nothing else in the universe besides us in this wire. If the electron's moving with velocity v down the wire, and I'm moving with a velocity v, to me it looks like that electron's not moving, right? It's exactly the same as when you're on the highway. If the car next to you is moving at the same speed, it doesn't really look like they're moving to you, right? Because they're just going with you, so it looks like you guys are not really moving at all. So to me, if I'm moving with speed v, it doesn't look like this electron is moving, right? So if I have just a static electron sitting somewhere, I know that it emits an electric field, right? So just think back to like, Q over 4 pi r squared from our electric field. So it looks like this one is just emitting an electric field, of a point charge in all directions, and that's it. So now if I'm moving with speed v, it looks like I have an electric field here. But now what happens if I stop moving? So let's say I stop moving, and now I stop moving, so let's get rid of this electric field. And since it's a wire, there's a bunch of electrons, let's say they're all moving down the wire with speed v. Well, now it looks like a steady current, right? Because now we're sitting still. It looks like there's a bunch of electrons moving down the wire, which looks like a current. And we know that a steady current, will cause a magnetic field. So now it looks like there's a magnetic field looping around the wire. So we're going to have a magnetic field going this way. So in one reference frame where we were moving, it looked like an electric field. And then in another frame where we were not moving, we were at rest, the same thing looks like a magnetic field. So that's a little bit, and again, I simplified a lot and skipped over some things that if you're doing this like the proper way, you wouldn't skip over, but this is just to give you an idea for how relativity sort of comes out of Maxwell's equations naturally. And if you take, 112b, you'll see how in some cases you'll actually do the relativistic transformations where you see how in one reference frame, something that's an electric field is actually a magnetic field in another reference frame and vice versa. So now let's look at Maxwell's equations in a little bit more detail. So you've probably seen in 7D, you probably saw Maxwell's equations in integral form, which is where we have this, right? So integral form is usually the form that they introduce it, like in your introductory physics class, but then once you get beyond that, they always use the differential form here. So I know not all of you have taken like multivariable or whenever they introduce like divergence, curl, gradient, all that stuff. But Maxwell's equations are much better understood and they're much more intuitive in this differential form because kind of, looking at something like this, like I can't look at these equations and immediately know what sort of field I'm looking at. Whereas once you understand what divergence and curl are, which are right here, then you kind of can just look at this and immediately know what these equations represent. So let's just go through each one a little bit more carefully. So here we have, this is our good old Gauss's law. So here, this is called the divergence. So all this is telling us, and again, it doesn't matter if you haven't learned this in calculus or anything, all this part of the equation is telling us, it's just telling us what the field looks like. Does it diverge away from a certain point or not? So a field that looks like this, so let's say we draw a vector field that looks like this. This has a divergence because it looks like all the vectors are diverging away from a single point. And a vector field, let's say, that looks like this, it's like uniform, this does not have a divergence because the field is uniform everywhere, right? So if I drew a bunch of arrows like this, it doesn't really look like they're diverging away from a single point. So this divergence would be 0, and this one would be non-zero. So all Gauss's law, all this equation is telling us is that electric field lines diverge away from a positive charge and will, kind of go towards a negative charge, right? If this was, let's say, a negative point charge here, these arrows would be oriented the same, but they would just be going towards the negative charge. So that's all this equation is telling us, is that this is what your electric field for a point charge looks like. Now, this equation doesn't really have a name, but all it's telling us is that the magnetic field here, there are no magnetic monopoles, right? So when we did magnetism in 7D, we learned that there were no magnetic monopoles, right? We saw that there was nothing where, there was no like point magnetic charge where the magnetic field kind of diverged away from the charge, right? This didn't exist for our magnetism. We only had magnetic dipoles, right? We only had, like if you had a bar magnet, we only had magnetic fields that would go like this. And that's because the divergence of a field like this is 0, because there's no single monopole, no single point charge. So that's all it's telling you. It's just telling you that the magnetic field will never seem to diverge away from a single point. It will always at least look something like this, like a magnetic dipole. And now this equation, so this here is called the curl, and it just tells you how much this field curls. Does it curl around something or not? So for example, what we had here, there's no curl here because these vectors aren't curling around anything. So when we did like Faraday's law and Lenz's law, that comes from this equation. Because remember, for when we did Faraday's law, we would have, like some wire, and there would be some magnetic field that was changing, some magnetic flux, right, through the wire. And then it would induce an EMF, it would induce a current circling around that change in the magnetic field. So we had a time-varying magnetic field in whatever direction, and we would induce an electric field that curled around it. So all this equation is doing is telling us that here we will induce an electric field that's curling around the changing magnetic field. And that was basically all Faraday and Lenz's law were. Oops, sorry, I forgot. This should be the other way because it's a negative sign. So it should be going that way. Okay, and then we have a similar kind of rule for the magnetic field. So this one is like Ampere's law, basically. So here, J is just the current, and we remember when we had, if we had a current, let's say, going this way, so if we had some current density going this way, we know that the magnetic field would curl around it, right? And we would use our right-hand rule, so the magnetic field would curl around it. So that's all this equation is telling us. It's telling us that the magnetic field curls around a current, and it will also curl around the changing electric field. So there's a really good 3 blue 1 brown video about Maxwell's equations here. If you're interested, I would definitely recommend, especially if you're a physics major or a math major too, I would definitely recommend watching it because it's really good. Gives you a really good visualization of what Maxwell's equations are actually doing. All right, so now let's talk about electromagnetic waves. So as we saw in like 7D, we know that a point charge will produce a static electric field, right? And we also know that a steady current will produce a static magnetic field. But what if we have a point charge that's oscillating? So if we have a point charge, let's say that's moving back and forth, it will actually emit electromagnetic radiation or electromagnetic waves. And actually any accelerating charged particle will emit electromagnetic waves. So if you have a particle that's just moving back and forth, it's obviously going to be accelerating because it's changing direction and changing velocity. So if you just have something moving back and forth, a charged particle, it will emit an electromagnetic radiation. Similarly, if you have a charged particle like an electron moving in a circle, it will also radiate away electromagnetic energy or electromagnetic waves. And this was actually one of the big problems when they were developing quantum mechanics, was we knew that moving charges that are accelerating emit radiation, they lose energy. And in the theory, we had of an atom, we have that an electron is circling the proton, is circling the nucleus, right? And we know in circular motion, you're accelerating the whole time. So the big problem was, well, why don't the atoms collapse if the electron is constantly moving and constantly accelerating? It should radiate away all of its energy. So why is the atom stable if it seems like the electron should actually lose all of its energy and just kind of fall into the nucleus? This is one of the problems that sort of led to the development of quantum mechanics. And here we can see the electric field for a moving charge. So here, let's say this charge is just moving back and forth, very tiny. This is the electric field lines it will create. So those are kind of ugly. So very close to the charge, it will create these weird lines. And then these are only the electric field lines. The magnetic field lines will be coming out of the page. They're going to be perpendicular coming out of the page. So this is just to see kind of what sort of field we create with a moving charge up close. But we're obviously not going to be looking at fields exactly like this because it's a little too complicated. So now the simplest way, like I said, to create electromagnetic waves or electromagnetic radiation is by having a charged particle oscillate back and forth in simple harmonic motion. So our buddy Hertz actually first studied electromagnetic waves in the lab about 20 years after Maxwell developed his theory. And he was actually able to first measure the wavelength, the frequencies, and prove that electromagnetic waves were in fact light waves and measure the speed of light. And he did that using an LC circuit, which in 7D you might or might not have gotten up to, but it's basically just a circuit with a capacitor and an inductor, and it can oscillate. So that was how he measured the velocity of light. So now that we know that electromagnetic waves are obviously waves and that they travel at the speed of light, we should be able to derive a wave equation, right? So here is using the differential form. I derived the wave equation for just the electric component, so just the electric field part of the EM wave. You would do basically the same thing. You would just take a different start with a different Maxwell's equation here, and then you could derive a similar equation for the magnetic field. So obviously I don't expect you to do this. This is just to show you that you can in fact get a wave equation from Maxwell's equations. Because we see here we start with one of Maxwell's equations, we do some manipulations on it, and we end up with here a wave equation. This just means a derivative. So here we have a derivative, and then we have 1 over the velocity squared, and then the double time derivative of our field, which was exactly our wave equation that we saw in chapter 14 or 15. So we have a wave equation here, and we can see that it's a wave that travels at the speed of light, c. Now your book has the derivation for this, not using vector calculus here. I don't personally, usually I would recommend that you always go through the derivations in your book. I don't think that this derivation is really worth going through because it's doing it without the curl and divergence, doing it without vector calculus is unnecessarily difficult. It's very easy. As you can see, it only took me 5 lines to derive it here. It takes like a page and a half in the book. So I would say it's not really that instructive to derive it yourself. Wait till you take like 112B or something like that, or vector calculus. Then it's much easier, and you'll be able to get a lot more out of it. So for now, you can just take my word for it that you can get a wave equation out of Maxwell's equations. So now one of the really interesting things about Maxwell's equations is, now you can see here I put in the speed of light c, but Maxwell's equations don't involve the speed of light, right? Nowhere here do I have c. I only have mu naught and epsilon naught, which are the magnetic and electric constants. And yet I was still able to figure out that they were waves that traveled at the speed of light. So what this tells us is that you can actually do a pure magnetism experiment, so do an experiment that involves only magnetic fields, measure the value of mu naught, then do an experiment that only uses electric fields, measure the value of epsilon naught, and from just those two experiments, you can calculate the speed of light. So the speed of light is actually related to epsilon naught and mu naught by this equation here. So C is equal to 1 over the square root of epsilon naught times mu naught. And now our C, as we said before, is 3 times 10 to the 8 meters per second. And this is something that you should absolutely memorize. Every physicist, every engineer should definitely have the speed of light memorized as 3 times 10 to the 8. Now, obviously, it's not exactly 3 times 10 to the 8. It's like 2.99 something. But 3 times 10 to the 8 is more than sufficient for essentially all problems we're going to do. So you can always use 3 times 10 to the 8. And then we just have epsilon naught, which we saw in 7D, is just a constant equal to this here. And then mu naught, we also saw in 7D, was just equal to this constant number here. So now let's talk about the electromagnetic spectrum. So the electromagnetic spectrum refers to all wavelengths or all frequencies and wavelengths of electromagnetic waves that we have, in the world. So at the very, very long wavelengths, so here we're looking at wavelengths that are like tens of meters. Those are radio waves. So radio waves are very, very long. And then we start getting into microwaves, which are about a centimeter in wavelength. Then infrared is a little bit smaller than that, about 10 to the 5, 10 to the negative 6. And then here we have the visible light spectrum. So visible light is obviously what's visible to us. It's what we can see. So it starts at around, 350 nanometers is the shortest wavelength that we can typically see, is around 380. So 380 nanometers is like violet, purple. And then the higher wavelengths here around like 750, 740 nanometers are like the highest wavelength that we can see. And different animals can see different wavelengths, like a lot of birds and insects can see in the infrared range, and they don't actually see in the visible light range. So the visible light is obviously specific for humans and other mammals like us. I think dogs can only kind of see in this range. They sort of only see like blues and violets and stuff. They don't see all the colors that we see. And then as we get past the visible lights and we go into even smaller wavelengths, then you get into the ultraviolets. That's the UV light. So you always hear about that with like sunscreen and stuff. It's the UV light that damages your skin, damages your eyes, all that stuff. So ultraviolet is over here. Then we get into X-rays here. So now we're at very, very small wavelengths, 10 to the negative 10. So this is even less than a nanometer. So X-rays are very, very small wavelengths. And then down here, gamma rays are the shortest wavelengths that we have. And typically, the shorter the wavelength, the more damaging, the more dangerous that type of radiation is to humans. So you definitely, X-rays, if you ever got an X-ray, they put like a big lead vest on you. It's because X-rays are typically, you don't want a lot of X-rays going through your body because they can damage your tissue, damage like your DNA. So the higher the wavelength, the worse it is, and you definitely don't want to get like showered by gamma rays because that would be very bad. And that was also one thing that they were very worried about with astronauts. Gamma rays are sometimes, you'll also hear them referred to as cosmic rays. They were very worried sending astronauts into space what the damage would be from cosmic rays, because our atmosphere typically shields us from cosmic rays and these other very high energy electromagnetic waves. And we really didn't know what would happen if you put a person outside of the atmosphere and they were kind of bombarded with these cosmic rays. Okay, so that's light. So let's just do a really easy example with the speed of light. And also just to kind of see how big space is. So here we have this example. How much time does it take light to travel from the moon to the Earth, which is a distance of 384,000 kilometers? So let's do that first. So we can obviously use our velocity equals distance over time formula. Here we have the distance and we're looking for the time. So the time is just going to be the distance over the velocity. So the distance is 384,000 times 10 to the 3, because it's given in kilometers, and then divided by the velocity, which is 3 times 10 to the 8. And I'm actually just going to change this to 3.84 times 10 to the 8, because this is 10 to the 5, and then I have another 10 to the 3 from the kilometers. So we can see here that our 10 to the 8 will cancel, so we're left with 3.84 divided by 3, and this gives us 1.28 seconds. So it only takes light about 1 second to get from the moon to the Earth. So like when they were sending astronauts to the moon, there'd be like a 1 second delay when they were communicating. So that's not too bad. So now let's see if the light from the star Sirius takes 8.61 years to reach the Earth. How far away is Sirius? So now we have, we're looking for the distance. So now we have that the distance is equal to the velocity times the time. So the velocity, we know, is still 3 times 10 to the 8. And now the time, we're given 8.61 years. And so now we're going to have to convert that to seconds. So in 8.61 years, let's see, we have 365 days in 1 year. And then in 1 day, we have 24 hours. And then in 1 hour, we have 60 minutes. And then in 1 minute, we have 60 seconds. So now we're to seconds. So we just multiply all this out, and we get, so this is actually, so this part is actually equal to 2.71 times 10 to the 8 seconds. And then we have 3 times 10 to the 8, and then multiplied by this. So we actually get that the distance is 8.13 times 10 to the 16 meters. Oops, 16 times 10 to the 16 meters. So that's obviously very far. And another thing to keep in mind, you might see some problems like this that use the word light year. So we know that, I'm sure we've all heard of light year, like watching, pop science shows or something. But it's very important to keep in mind that light year is a unit of distance, right? It's how far light travels in 1 year. So if you ever see a problem that uses light year, you know the velocity, the speed of light, is 3.10 to the 8th. So you have to figure out how far can something going that fast travel in 1 year. And that's a light year. It's a unit of distance, not a unit of time. I see a lot of students make that mistake when they see light year. They just kind of put in 1 year, but it's a unit of distance. And it's obviously like a huge unit of distance, like a couple trillion miles, something like that. All right, so now let's talk about actual electromagnetic waves quantitatively. So what we're going to be using, we're going to be using like a nicely behaving EM wave, because we saw previously you can get kind of some weird looking things if you're up close to the particle it's moving. But when you're far away from the particle, the waves start behaving like very nicely, and they sort of just look like our transverse waves on a string. So these are called plane waves. So this is essentially what an electromagnetic plane wave looks like. You have the electric field in one direction. So here our electric field is in the y direction. The magnetic field is perpendicular to that, in this case the z direction. And they oscillate in phase with each other with the same frequency and the same wavelength and obviously the same velocity. So this is an electromagnetic wave. So the electric part, the electric component, oscillates just up and down in the y direction, just like if you had a string oscillating. And then the magnetic field oscillates in a direction perpendicular to that. And now here, the magnetic field is drawn so that it looks like it has the same amplitude as the electric component. That's not totally accurate. They're actually related. And again, your book has a derivation for this, which I don't really think is like that illuminating, so you can kind of just take it as a given. The electric and magnetic field are related by C. So the electric field is actually C times greater than the magnetic field, right? Because I can rewrite this as E equals CB. So for a electromagnetic plane wave, the amplitude of the magnetic field times 3 times 10 to the 8th is equal to the amplitude of the electric field. So, if we were going to draw this accurately, you wouldn't be able to see the magnetic field. So they're typically drawn so that they look equal, but just keep in mind that they're really not. The magnetic field is significantly weaker in these waves than the electric field. And also just in general, the magnetic field is typically much weaker than the electric field. And that's because the magnetic field is actually just a relativistic effect. So this is, obviously we're not going to get into relativity in this class, but if you do take any more physics classes, it's really, really interesting to see how the magnetic field sort of arises directly as a consequence of relativity. So anyway, that's why the magnetic field is significantly weaker than the amplitude of the electric field, just because it's a relativistic effect. So just keep in mind that our electric and magnetic fields, the ratio of them, electric to magnetic, is equal to the speed of light. So now we can start to write our wave function for this plane wave. So we know that electromagnetic plane waves are transverse waves, and we can see that just from looking at this diagram. We also know the wave function for a transverse wave, right? We already wrote that in like chapters 14, 15, and 16, so we know what this looks like. And now here, so this is the wave function for a wave traveling just in the x direction, obviously. And now here we can see that our wave, the electric field, only has a y component, right? So the electric field just has a y component, it's pointing in the y direction, and the magnetic field only has a z component. Now, in real life, your plane wave can not just be dependent on x, it could be dependent on x, y, and z. So this is like a very simplified case that we're going to be using. So let's just say we have one component one component for the electric field, one component for the magnetic field, and let's just write our equation for that. All right, so here we're going to have exactly the same equation as we had in chapter 15, but now it's actually a vector. Because we know that our electric and magnetic field are both vectors, so we just have to add in our vector to show which direction the electric field component is in and the magnetic field component. So here, since we said the electric field in our previous little diagram right here, we said the electric field just had a y component and the magnetic field just had a z component, and we can see it's traveling in the x direction. We can just write our wave function like this. So E here is the maximum amplitude of the electric field, B just refers to the maximum amplitude of the magnetic field, and then we just add in a j hat to show the electric field is in the j direction, and k hat to show the magnetic field is in the k hat or z direction. And as we said before, these waves oscillate in phase, and they oscillate with they have the same k because they have the same wavelength, and the same omega because they have the same frequency. So for our purposes, the k and the omega will always be the same for our electromagnetic waves. And then another very important thing about EM waves, EM plane waves, is that the direction of travel for the wave is always the cross product between the electric field and the magnetic field. So here we have E is in the y direction, B is in the z direction, and then it's traveling in the x direction, because if you do y cross z, that gives you x. So the E field cross the B field will always give you the direction of travel for your EM wave. And now it's very important here, remember that the cross product is not commutative, so it's very important to not do B cross E. You have to do E cross B. So let's just do a quick review of the right-hand rule, because I know a lot of people don't like the right-hand rule. So the first thing to remember about the right-hand rule is that it's not commutative. So if you have A cross B, that is not equal to B cross A. You actually would get an extra negative sign if you swap them, so that's why you have to be really, really careful with your order for the cross product. You can't change the order that the vectors are in. And the other important thing to remember for the cross product is that it takes two perpendicular vectors. So remember, your A and B for a cross product have to be perpendicular. If they're parallel, your cross product is going to be 0. So it takes two perpendicular vectors and gives you a third vector that's perpendicular to both of them. So now you have three mutually perpendicular vectors. So for example, so let me just write here. So like if A cross B, so if A cross B is equal to C, then that means that A and B and C are all perpendicular. And now that's important to keep in mind, because that means if you have an electric field that's in the J direction, your field, or your wave, sorry, cannot be propagating also in the J direction. It has to be propagating, in this case, either in the positive x hat direction or the negative x hat direction. And you would figure that out, whether it's positive or negative, from doing E cross B. So in this case, it's obviously the positive x direction. And just like an easy way to do cross products, if you haven't seen this before, you can always just quickly do the cross product of your 3 or 2 vectors by writing out like I, j, k like this. And then if you do I cross j, that gives you k. J cross k gives you I. K cross I gives you j. So you just go around this little circle like that, doing your cross product. And then if you do it backwards, so let's say if you do k cross j, that just gives you a negative. So k cross j would be negative I, j cross I would be negative k, and so on. So that's just like a really easy way to do the cross product, and that works for any coordinate system. So if you were in spherical coordinates with like r, theta, and phi, you could do the same thing. You put r, theta, and phi here. And the same with cylindrical coordinates with r hat, phi hat, and z hat. You put r, phi, and z. So anyway, so that's how you take, that's just a reminder on the cross product there. And then if you want to do it with your hand, obviously, just to recap, you point your hand. So let's say we have our first vector in, going into the page like this. So you put your hand in that first direction. Then you turn your fingers pointing in the direction of the second vector. So if my second vector is going this way, I would just point my fingers in the direction of the second vector, and then my thumb points in the direction of my third vector, my resultant vector. So you just do, your hand like this. That's the way that I like it better. I think that's easier than like with the fingers. I don't know, it's easy to like not point your fingers in the right direction. But I like it better with your hand. You just put vector 1, turn your fingers vector 2, and then your thumb points vector 3. Very easy. So now let's do just a little bit of an example. So let's say here we have our electric field is obviously pointing up. We want to turn our hand, our fingers, right, in the direction of the magnetic field, which is kind of pointing like to the side this way. And so then our wave is propagating in this direction. So if you do E cross B, you get that direction like kind of out of the page. And then if you do your right-hand rule for this one, you'll see that you end up getting the same direction because you can do E cross B, still out of the page. All right, so now let's do an example with our EM waves. So we have a laser emits a sinusoidal EM wave that travels in the negative x direction. The wavelength is 10.6 micrometers, and the E field is parallel to the z-axis with the amplitude being 1.5 megavolts per meter, right? The wave function for the electric and magnetic field. So let's just first write our lambda is 10.6 times 10 to the negative 6 is micrometers. Our E max is 1.5 times 10 to the 6 is megavolts per meter. And the electric field is oriented in the z direction. So, okay, so we want to write our electric field. So the electric field is going to be that E max, then cosine kx, and it's traveling in the negative x direction. So remember, for our waves, if it's traveling the positive x direction, it's kx minus omega t. If it's traveling in the negative x direction, it's kx plus omega t. So this gets a plus omega t. And now we just have to find k and omega. So k is going to be equal to 2 pi over lambda. So we just do 2 pi over lambda is 10.6 times 10 to the negative 6. So we get, let's see, 5.9 times 10 to the 5th radians per meter for k. And then for omega, we know that omega is 2 pi times the frequency. And we know that the frequency, we know that the velocity of a wave is lambda times f, right? The wavelength times the frequency. And we know the velocity here is c. So we can just easily rewrite the frequency as c over lambda. And we'll get 2 pi times c over lambda for the angular frequency omega. And now we're just going to plug in the values, 3 times 10 to the 8 for c, and then lambda we said was 10.6 times 10 to the negative 6. So now we get for omega is 1.8 times 10 to the 14 radians per second. So now we have everything for our wave. Let's just add in here, we said it was traveling, it's parallel in the z direction, so we're going to give it a k hat here. So this is basically our wave equation. So Emax, so if we wanted to just write that all out, we would just say, E is equal to Emax, where Emax is 1.5 times 10 to the 6. Then cosine kx, where k is given by this, plus omega t, where omega is given by this, and that's in the k hat direction. Now we want to find the magnetic field, or the magnetic wave function. So we know it's going to be Bmax cosine kx plus omega t. And the first thing is we need to know, well, what direction is the magnetic field in, right? So we know that we're going to have E cross B is the direction of travel, which we said was it travels in the negative x direction. So that's going to be negative x. And we know that the electric field is K, sorry. Yeah, K. The electric field is K. So I'll write K hat times, or cross what, is equal to negative I hat. So you can just draw your little cross product circle here. And we say, okay, K hat cross what will give us negative I hat. And you can see K hat cross J hat will give you negative I hat because you have to go counterclockwise. So that means that this right here is J hat, and our our magnetic field is in the J hat direction. And then we just have to find what Bmax is. So we know that the electric and magnetic field are related by C. So that just means that Bmax is going to be equal to Emax over the speed of light. So we had 1.5 times 10 to the 6, and then we have 3 times 10 to the 8 for the speed of light, and so that will give us 5 times 10 to the negative 3 Tesla. So you can see the magnitude of the magnetic field is much, much lower than the magnitude of the electric field. We basically have 10 to the negative 3 versus 10 to the 6. So that's our, then we would just have to plug these numbers in. So for Bmax, we would just put this. K, we already found it's the same K is right here, and the same omega because the waves are in phase with the same wavelength, same frequency. Now this next problem is very similar, but it's maybe a little bit harder. All right, so here we have a sinusoidal electromagnetic wave in a vacuum, has the magnetic field amplitude 4.3 times 10 to the negative 3 Tesla, and a wave number of 2.5 times 10 to the 6 radians per meter. At a certain position in time, the electric field E points in the negative y direction, and the magnetic field B points in the positive x direction. So the first thing we want to do is find the amplitude of the E field. So that part is easy. We know all we have to do is just multiply the B field by C, right? Because we know the electric field is C times B. So all we have to do, they give us the magnitude of the magnetic field. So we just have to multiply the 4.3 times 10 to the negative 3 to get the electric. And that comes out to 1.29 times 10 to the 6 volts per meter for the electric field. Then we want to find the wavelength. Well, they give us the wave number, so they give us that K is 2.5 times 10 to the 6 radians per meter, and we know that K is equal to 2 pi times lambda, which means that lambda will be equal to 2 pi over K. So all we have to do is just divide 2 pi by the wave number, and we get 2.51 times 10 to the negative 6 meters. So let's just circle those things. So that's the wavelength. And then for part C, we want to find the frequency. So for part C, so now the frequency, again, we can use this V is equal to lambda times F. So we know V and we know lambda. So the frequency is just equal to V over lambda. So again, we have 3 times 10 to the 8 over 2.51 times 10 to the 6. And so that gives us for the frequency 1.19 times 10 to the 14 hertz. Okay, and then for the last part, we just want to find the direction of wave propagation. So the direction of the wave propagation we know is going to be E cross B, and E, they said, points in the negative y direction, so this is negative j, and B points in the positive x direction. So negative j cross I, so write your little circle. Now if you have a negative sign here, oops, what you do is just ignore the negative sign for a second and do j cross I. So j cross I would give us negative k. So we'd have j cross I is negative k hat. And then we can just add this negative sign back in, and then we'd have a negative times a negative, which gives us a positive. So this is equal to positive k hat. So our direction of travel is in the positive z direction. All right, so let's do one more example with this. Now this is a good one to give a try yourself. It's a little bit harder. So, give it a try. If not, just keep watching and we'll go over it in a second. Okay, so this problem, we have an electromagnetic waves has an electric field given by this equation, obviously in the k hat direction. So in which direction is the wave traveling? So here we have to look at the wave function they give us. So here they give us kx minus omega t. So since ky. So here they give us ky minus omega t. So if we have a wave where the wave function is ky minus omega t, that means it's traveling in the y direction, right? Just like when we had kx minus omega t, that meant it was traveling in the positive x direction. So here our wave is traveling in the positive y direction now. And you notice E is a function of y and t, not x and t. Now, what is the wavelength of the wave? Well, you might think at first, get stuck that k is not given to you, and normally we would use k is equal to 2 pi over lambda to find the wavelength. So if this was just a problem with a transverse wave on a string, we wouldn't be able to find the wavelength unless we knew like the linear mass density of the string and the tension. But here, because we know the frequency, and we also know that all electromagnetic waves travel at the same speed, they travel at the speed of light, we can actually figure out lambda without k. So we can instead use the velocity as lambda times the frequency, where the velocity, let's see, so lambda is going to be equal to c over f, and we know that the frequency and the angular frequency are related like this. So that means we can rewrite the frequency as omega over 2 pi. So then we can just plug that into this equation and write lambda as c over omega times 2 pi. So now I can just plug in 2 pi times 3 times 10 to the 8th over omega, which we do have, which is 10.5 times 10 to the 12 radians per second. So this comes out to 1.8 times 10 to the negative 4 meters. So that is the wavelength. And then write the vector equation for B. So let's do that here. So that was part C. So B, we know, will be B max cosine ky minus omega t. Now B max. Now let's find the direction of B first. So we know that the wave's traveling in the positive y direction, and E is oriented in the positive z direction, the k direction. So E cross B is going to be equal to j hat, and E is k hat. So k hat cross what is equal to j hat? Well, just look at our little circle here, and we can easily see that k hat cross I hat is equal to j hat. So this is I hat. So our B is in the I hat direction, the x direction. And now let's find the value of B max. So we know that E over C is going to give us B. So E we had was 3.6 times 10 to the 5. Yep. and then c is 3 times 10 to the 8. So this gives us 1.2 times 10 to the negative 3 Tesla. So this is our B max here. And then K, we're just going to need to find K is 2 pi over lambda. So that's 2 pi over the wavelength we just found here. So that was 1.8 times 10 to the negative 4. And so that comes out to 3.5 times 10 to the 4 radians per meter. And then we can just plug all of that into this equation up here because we know it travels in the I hat direction. For B max, just plug this in. For K, plug this in. And then for omega, it's going to be the same value as right here. And that will be your equation for B. All right, so now let's look at the speed of light in dielectrics, or in matter. So once light enters a medium, usually we call it a dielectric, it's going to change the velocity. So it will slow down. We know that the speed of light, nothing can ever go faster than 3 times 10 to the 8th. That's like the ultimate, as part of Einstein's relativity, that's like the ultimate speed limit. It's a physical constant. So no matter how fast you're going, you could be going half the speed of light. If you look at a beam of light, it will still look like it's going 3 times 10 to the 8 meters per second. So no matter how fast you go, you will always see light in a vacuum traveling at 3 times 10 to the 8 meters per second. So that was part of Einstein's relativity. But if you're in a medium, so if you're in like water or some kind of any kind of material like diamond or any kind of translucent material, the light will slow down. So remember when we did dielectrics, we had epsilon instead of epsilon naught. So when you're in a dielectric, you replace epsilon naught with epsilon. And there's a similar thing for magnetism. So when you're in a material, you go from mu naught to mu. So it's the same idea. And then remember, we could also write epsilon as the dielectric constant K times epsilon naught. There's also a similar equation for mu, where we have mu is Km, where Km is called the relative permeability of the material. So it's just Km times mu naught. So it just, these constants just tell you how electricity and magnetism behave once they're in the material. But you don't need to know any, we're not getting into K and Km and all that stuff. For most problems, they'll just give you the values. So the only thing that you really need to know is that it slows light down. So in a dielectric, the speed of light is no longer c, it's actually 1 over mu times epsilon square root. So instead of mu naught times epsilon naught, we have mu times epsilon, where mu and epsilon are given here. Now, if I just wanted to write this out a little bit, let's say I had V is equal to, so I have V is equal to mu times epsilon, and then I can rewrite this as mu is Km times mu naught, and epsilon is K times epsilon naught. And then I can separate out the mu naught and epsilon naught and the K's. So I can rewrite this now as 1 over Km times K times 1 over mu naught times epsilon naught. And now this we know is equal to C, right? So this is actually just equal to C. So I can write this as C over Km times K, where these are just the constants of the dielectric. So you can see here that the speed of light is decreased now to some new velocity depending on what these constants are. So I can just rewrite this as, let's just rewrite this as C over V. So we just want the ratio of the speed of light in a vacuum to the speed of light in some medium. We can rewrite this as Km square root Km times K. So this is called the index of refraction. So this ratio of C over V is called the index of refraction, and we're going to be using this a lot, especially when we get more into optics. We're going to be using the index of refraction all the time. So it just tells you how much does light slow down in this medium. Now, one really interesting thing that you can have is what's called Cherenkov radiation. So this happens if you have, let's say you have some material where light slows down, a good amount. Now you can have electrons in your material actually move faster than the light in the material. So this happens a lot in nuclear reactors. They give off this like blue glow, which is called Cherenkov radiation. And it's because the electrons in the material are moving faster than the light in the material. And now it might seem like this is violating relativity because originally we said, well, nothing can move faster than the speed of light. But this actually doesn't violate relativity because it's only the speed of light in a vacuum that is the ultimate speed limit. So if you're not in a vacuum, you can actually have things that move faster than light in that medium. So the electrons here are not moving faster than 3 times 10 to the 8. The light is slowed down to, let's say, 1 times 10 to the 8, and the electrons are just moving at 2 times 10 to the 8. But they're still moving slower than light in a vacuum. Okay, so anyway, so that's just a cool effect of light slowing down in some mediums. So let's just do an example. So here we have, we have a diamond, and we're shining light through it that has a frequency of 5 times 10 to the 14 hertz. We want to find the wavelength in a vacuum, so let's just do that first. So that we know right away. We can use C is equal to lambda times F, where lambda is C over F, so we have 3 times 10 to the 8. The frequency is 5.09 times 10 to the 14. So that's going to give us 5.89 times 10 to the negative 7 meters. So that is our wavelength in a vacuum. And now we want to find the wave speed, so the speed of light, and the wavelength in a diamond now. So when we have some medium there, and we're given the index of refraction, we're given K and Km in a diamond. So for that part, we know that the velocity changes by this amount, right? And now here, Km is just equal to 1, so we're just going to do 3 times 10 to the 8 over K, which is 5.84. And so that comes out to 1.24 times 10 to the 8 meters per second. So you can see, like, this number out here is like halved. Obviously, we still have the 10 to the 8, so the speed isn't really halved, just this, this one number out here. So it does slow down when we're in diamond. And now let's find the wavelength. So the wavelength is going to be the velocity in diamond, so that's slowed down velocity, divided by the frequency. Now the frequency doesn't change when you go into a new medium. When we do optics, we're going to see why in a little bit more detail. You can probably figure out why now, so if you want to start thinking about why the frequency of the light doesn't change when you enter a material, even though the wavelength and the velocity do, you can start thinking about that now, but we'll go into it more when we do optics. So anyway, let's plug in our velocity, which is 1.24 times 10 to the 8. And then the frequency stays the same, at about 5 times 10 to the 14 hertz. So the wavelength comes out to 2.44 times 10 to the negative 7 meters. Okay, and now for part B, we have a 90 megahertz radio wave that passes from the vacuum into an insulating ferrite, which is just a ferromagnetic material used in computers to suppress interference. So we want to find the wavelength in vacuum, just like we just did, and the wave speed and wavelength, again, in this material. And now here, K is about twice as big, and now Km is 1,000 instead of 1. So let's do part B here. So for part B, we want to find the wavelength in a vacuum. So the wavelength is going to be C over the frequency. So we've got 3 times 10 to the 8. The frequency was 90 times 10 to the 6 because it was megahertz, so it's 10 to the 6. So this gives us 3.33 meters. All right, so that's our wavelength, and now we want to find the speed of light in this material. So we know that the speed will be decreased by k and km. So we have 3 times 10 to the 8, and then we said k was 10, and then km was 1,000, so that's 10 to the 3. So the speed of light now will actually be decreased to only 3 times 10 to the 6 meters per second. So the speed of light there is significantly decreased. And now let's just find the wavelength in this material. So we can use lambda is equal to the velocity in the material divided by the frequency. The velocity is now 3 times 10 to the 6. The frequency we said doesn't change. That's going to be still 90 times 10 to the 6. And for that, we get the 10 to the 6 cancel, we get 3 over 90. So we're going to have 3.3 times 10 to the negative 2 meters. So now we can see that our wavelength actually changed a lot, right? Because here we were at 3 meters, and now we're at 3 centimeters. So that's a big change. And also the speed of light did change a lot. So I know that going from 3 times 10 to the 6 to 10 to the 8th doesn't seem like that big of a jump because it's only 2 different. Let's just see what percent of the speed of light this is. So if you want to just find essentially what fraction of the speed of light that is, we have 3 times 10 to the 6 divided by 3 times 10 to the 8th. We're going to be left with 10 to the negative 2. So 10 to the negative 2 we know is 0.01, which is about 1%. So even though 3 times 10 to the 6 is still really fast, right? It's actually only 1% of the speed of light in a vacuum. So this material can slow light down a lot. Okay, so that's it for today. We're going to finish up. We're going to be doing power and intensity for electromagnetic waves. I know no one liked that for sound. Hopefully for the EM waves it will be a little bit better. So we're going to be doing that next time and also see some applications of EM waves in everyday life. So all right, I will see you guys on Thursday.